Hey class, Adam Ward here. This is our second lecture recording on the topic of open channel flow. And in this video, I'm going to introduce the concept of specific energy. So for thinking about specific energy, let's start by idealizing some system with flow going from point 1 to point 2. And since this is an open channel, let's imagine we have a stream bed that has higher in elevation at point 1 than it is at point 2. So flow would be from left to right across the screen. We've got a water surface somewhere up above that. That would be, of course, our hydraulic grade line. And somewhere up top then we've got an energy grade line. And of course that energy grade line is not horizontal because we do have friction, we have shear stress, so we're losing some energy as we propagate through the system. So what do we know? Well, one thing that we might do is describe the slope of that stream bed. And I'm using S sub 0 or S naught here. And that slope is the change in elevation divided by the length. And so just to label that in brown to be really clear here, that stream bed is at some elevation Z1 on the left, Z2 on the right, and the length is the distance between those 2 points. So that's a definition for a linear slope. Of course, if we're thinking about this the way we did hydraulic grade lines and energy grade lines, the next term we would add on there would be the pressure term. So P1 over gamma and P2 over gamma to define then where that water surface is. And that velocity head would be what's up above. Finally, the lost energy, right, that vertical distance on the right that I've illustrated in purple, HL for head loss. And the slope of that energy line, we're going to denote SF, and that's the head loss over length, right? The change in elevation per change in length. And that F I want you to think of as friction, right? So this is the sometimes called the friction slope in the channel itself. So what we're going to do then is take this setup where we have elevation head, pressure head, and velocity head, head losses, and use that to our advantage. Take our energy equation and sort of customize it for this part of the problem. So writing out our energy equation between those 2 points, we'd have the energy at point 2 on the left equals the energy that we started with for point 1 minus the head loss. And we're going to make a couple of substitutions here. And so instead of talking about pressure as P1 over gamma, we're going to describe it as the equivalent height of that column. So Y1 would be the depth of water at point 1. And similarly, we'll define Y2 at point 2. And we've got those definitions of slope. So taking our energy equation, we can substitute back in those definitions. So Y1 and Y2 now take the place of the pressure terms. The elevation terms have been wrapped up in the bed slope, and head loss has been replaced with the friction slope. And then in open channel hydraulics, we'll take this term, both the pressure head and the velocity head, and describe it as what we call specific energy with a capital E. So specific energy just means we're taking the pressure head, which was that depth of flow, and the velocity head, V squared over 2G, and we're going to rename it capital E. And so when we do so, we find the energy at the downstream point, or the energy at the upstream point equals the energy at the downstream point, and then we need to account for the head losses and the elevation changes. So that specific energy equation is nothing more than the energy equation we've already used. We've just changed a couple of terms. We added water depth, we grouped some things together as specific energy. Now let me show you why this is helpful to us. So there's our definition for specific energy up at the top. Specific energy is the pressure head, or the depth of fluid Y, plus the velocity head. And just for this slide, let's consider a rectangular channel that is the width B, and the depth of water, of course, is Y. And we know that would have a cross-sectional area then of depth times width. And a few other definitions here. We remember that discharge Q is equal to area times velocity. And we're going to define a lowercase q, which is the flow per unit width. And so this lowercase q is saying, hey, if you took 1 unit width of this, if you took just 1 unit width of the channel, what would the discharge there be? So if you take all of those and you do a little algebra, you can find yourself with this equation. So I've basically just replaced the velocity term with a definition about that uses the specific discharge, or that lowercase q. And we're actually in a place now where we can solve this. So if we look at the axes that I have drawn on this screen, so the horizontal axis labeled in red is going to be specific energy, and the y-axis is going to have that depth of flow on it. And it turns out that if we plot a solution to this equation, it looks something like this. So this is actually an equation that's third order in y, and we end up with these 3 solutions. So you'll see that I've drawn in gray a 45-degree angle. That's at the point where all of the specific energy would be depth, or in other words, along that diagonal, that would be the case if velocity were equal to 0. And that's not the case in an open channel system where it's actually flowing. So we get these 3 solutions. So what gives? There are a bunch of possible solutions then, right? So for every value of depth, there is exactly 1 value of energy that goes with it. But what's complicated is if you know the energy, there are 3 possible depths, right? So knowing the energy would be like drawing that vertical red line. And so there are 3 possible solutions for any energy that exists. Now, one of those is negative, and we're going to say that that's not physically meaningful. There's no such thing as negative 2 meters of flow. So we can dump off the negative solution, but that still leaves us 2 possibilities. So for a given amount of specific energy, flow could take 2 forms. It could take the supercritical form, where it's extremely shallow and fast, or it could take the subcritical form, where it's slow and deep. So specific energy lets us deal with both subcritical flows and supercritical flows. If we pick a given point on the horizontal, right? Again, the spacing from the vertical axis to where we cross that diagonal, that's the depth of flow. And then the distance you are to the right is the velocity head. So just to drive it home again, I'm redrawing over this in purple. Just to drive home, this distance from the diagonal to where you are on that specific energy curve, that's the velocity head. You might have also noticed that curve that you're interested in actually has a minimum to it. And that's the point that we call the critical point. That minimum energy condition is where you pass through Froude number equals 1. That's where you pass through critical flow. So we define that point as having some minimum energy state and some Y critical or YC value. So as you pass through that point, Froude number is going to equal 1. The minimum energy state is going to be 1.5 multiplied by the critical depth. And the critical depth can be defined as specific discharge squared divided by gravity. And then you take all of that and raise it to the 1/3 power. And so the idea here is that if you are in the band above critical flow, or if you're in the band up above critical, that's the subcritical section of the plot. Right? So if we thought of this, this red line, it's subcritical flow if you are above that red line, and it is supercritical flow if you are below it. So this critical flow condition is how we define the problem. Now, if we changed the amount of specific energy that we have, right? So if let's envision we were at point 1 and we took some head away from the problem. Maybe we changed the width, or we changed the roughness of the bed. We changed the specific energy, right? A change in specific energy must be accompanied by either a change in elevation, a change in velocity, or both. So you perturb the system and the depth responds. The thing that we don't know yet is how it actually responds. So just because we take energy away and we reduce E, we don't know if we reduce it and we get the subcritical phase or if we get the supercritical phase. So the next lecture video that I record, we're going to talk through a problem like this where we have a perturbation to the flow, and we're going to ask, how do we know if you were subcritical? Did you stay subcritical, or did you accelerate past that point to supercritical? And so we'll work through an example problem that will hopefully continue to get you familiar with specific energy diagrams and also help you understand how you can predict if something's going to be subcritical or supercritical. So stick with me for that. I will see you in a moment to work through it. Thanks all.